One of the most universally loved dishes, especially by kids, is this mac and cheese. And it's made out of this macaroni style pasta, which consists of this tubular design. So the cheese can deposit not just from the outside on this macaroni tube, but it can also flow inside and get deposited inside this macaroni tube, and that's one of the things that makes this dish so yummy. Now, the reason I'm bringing this up is that the channel which is used for making 3D NAND almost universally also follows this macaroni design. So what it consists of? It consists of this polysilicon channel, okay, and it follows this macaroni design, and it's laid out in this tube which is hollow, and inside this polysilicon channel, it's usually filled up with an oxide inside. Okay, it's filled with an oxide inside, and it's also surrounded by oxide. Okay, so just like this mac and cheese, this macaroni pasta over here, it's surrounded by cheese from both the outside and inside. This macaroni channel is made out of polysilicon, and it's surrounded by oxide both inside and also outside of this polysilicon tube. So let's understand why we use this macaroni channel. And there are two reasons. One is based upon the device design, and the other one is based upon the process. So let's understand the process argument first, why we use this macaroni channel. So I'm showing here a 3D NAND stack which consists of several of these control gates which are separated by this white oxide in between. And into it I have etched this hole into which I'll form my channel for my NAND transistor. And you can see that by virtue of this etch process, this hole is always going to be this shape where it's wider on the top and it's more narrower at the bottom, and it's just how all the etch processes work, that when you start the etch, you have more influx of ions or radicals which are creating this etch, and as you essentially go down the structure, that ion density decreases. So you always, when you open a plug like this, it would always be wider on the top and more narrower on the bottom. Okay, so now I'll initially fill it up with all these dielectric layer which would form my gate stack. So I might have an oxide, a nitride, and followed by another oxide deposited inside this plug first, and then would come the chance where I need to fill it up with the polysilicon which will form my channel. So when I start to filling it up with polysilicon, I essentially have two options. Okay, so I would essentially start filling it up with polysilicon, and this deposition would happen on this side, it would happen on this side, and again, I can keep filling it up with polysilicon. And I have two options. I can stop my deposition of polysilicon at this point, okay, and then what I would be getting is a channel which is like this. Okay, so it has a uniform width because this polysilicon is deposited uniformly on both sides, and I can control the width of this very precisely by controlling the amount of time for which I'm doing this deposition. So you can see that the width of the channel in this case is constant. Okay, so this is my option 1, and you can see that the width is constant. Okay, Now, I can keep on continuing with this deposition. I can keep on continuing with this deposition, and eventually I can fill up the whole plug. I can fill up the whole plug with polysilicon, and this would be my bigger and more voluminous option, and I can call it option 2, where I essentially have a solid plug made out of polysilicon, which is acting as my channel material. So what you notice in this case is that the width of this plug is not constant from the top to the bottom, and that's just because the hole that we were initially filling into had this profile where it was wider on the top and more narrower on the bottom. As a result of this, the width of this channel is essentially also much bigger on the top and smaller at the bottom. So if I make a stack using this second option where I have a solid plug, I see that the transistors which are at the top, they would see a much wider channel, and this transistor would have a much smaller resistivity, while the transistor at the bottom, it would see a narrower channel and it would have a more resistive path for current flow. But of course, you don't want this to happen. So a better option would be to have a profile like this where the width of the channel is constant, and my transistor on the top, they see essentially the same width and the same resistance, and my transistor is the bottom, they also see the same width, and the channel resistance is constant, which is much easier to control. Now, I said there are two arguments for doing this. I explained the process argument. The reason is that, although the device manufacturer might hate to admit this reason, but they can't produce a channel which is perfectly vertically etched, and hence the Macaroni channel design is preferred. There is also a strong argument on the device side. Okay, so let me explain why you prefer the Macaroni design even from a device design perspective. Okay, so I have again two options here. My option one, which is to essentially only fill this channel, only fill this polysilicon in this small thickness, and fill the rest with a dielectric and oxide. Or I have my option 2, which is to essentially fill the whole plug with polysilicon. Okay, so in option 2, what would happen is that this whole plug is filled up with polysilicon, and now the threshold voltage is controlled by a variety of things. It's controlled by the flat band voltage, it's controlled by the difference in the work function between the metal and the polysilicon. Plus, it's controlled by the amount of trap charge. Now, what happened in polysilicon, since it's not a single crystalline material, you have a lot of grains, and then in between these grains, you have grain boundaries. So, shown in these red lines over here are these grain boundaries. And these grain boundaries are active sites for trapping of charge, and you denote this by a trap density numbers, which happens to be pretty high. Usually, this number is much higher than the doping number that you have in this channel, okay, or the number of dopants that you have in these channels. So you have a large number of traps, especially if you have a non-crystalline or a polysilicon channel in this case. Okay, so because of that, the threshold voltage essentially has this extra term where it's dependent upon the total amount of traps which can be, which can essentially hold charge, and that would be determined by your depletion width. Okay, so let's say your depletion width is WD. The total amount of charge you can have would be the trap density times the depletion width. And this depletion width, if you remember from your device physics, it's an inverse function of the doping density plus, in this case, the density of the traps. And in this case, since the number of traps is much higher, you can say it's inversely proportional to the square root of the trap density. So overall, your threshold voltage is proportional to square root of the trap density, and this is a very large number for polysilicon material. So you can, what it results in is that you have a large variation in your threshold voltage when you have a conventional design where the channel is all filled up by polysilicon. So the threshold voltage, let's say in some region, if there are no traps, it could be lower, versus if in some region there are a lot of traps, it could be much larger, and it could vary in this large range, which again becomes very difficult to control. Okay. On the other hand, if you go with option one, which is the Macaroni channel, what you do is you have traps, but they're contained in the small thickness of the channel that I'm depositing. And my threshold voltage, it again depends upon this trap charges. But now the number of charges are no longer equal to the depletion width, but it's proportional to the number of traps multiplied by the thickness of the silicon. And I can keep making this macaroni channel thinner to essentially control the amount of variation I get in my threshold voltage. So again, in this case, I have a dependence which is controlled by the thickness of silicon. And if I again use a macaroni design where I only have a thin silicon channel, you see that the resulting distribution of this threshold voltages is much tighter. So this is the device argument for also using a macaroni channel.